Hi. In this video we're going to be going over something called the chi-squared goodness of fit test. Tests the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. The notation that we're going to be using, capital O, represents your observed frequencies of an outcome that's found from your sample data. Capital E represents the expected frequency of an outcome found by assuming that the distribution is as it's claimed. Lowercase k represents the number of different categories that you have. Lowercase n represents the total number of trials or observed sample values. When we're doing this test, the null and the alternative hypothesis are always the same. The null hypothesis will always be that the frequency counts agree with the claimed distribution, and the alternative is always going to be that the frequency counts do not agree with the claimed distribution. Our test statistic, it's clumsy to calculate by hand. We will do one by hand. It's quite easy to do on your calculators, however, so that's how I would expect you to do these. So the chi-squared statistics is equal to the sum of your observed minus your expected squared, and then divided by e. This is always a right-tailed test, and the degrees of freedom will always be k minus 1. This is just a flow chart that tells you what you would decide to do. So again, this is the chi-squared distribution. Remember, this is not symmetric like the normal distribution and the t-distributions are. It's also not centered around 0. It starts at 0 and goes up to positive infinity. So there are a couple of differences there with this distribution and the ones that we've worked with the most. So what we want to do is compare the observed values to what we expect. If the observed and the expecteds are close, then you'll end up with a small chi-squared statistic, which will give you a large p-value. So this marker is your critical value. And remember, with any other tests, so this is a right-tailed test always, so if your test statistic is in this region, then we're going to decide to fail to reject, and that will tell us that it's a good fit with the assumed distribution. If the observed and the expecteds are not close together but far apart, then we will expect a large chi-squared statistic with a small p-value. And again, this is our critical value. And so if your test statistic is in this region, then we would reject the null hypothesis and assume that it was not a good fit. So remember, the null hypothesis is that the data fits the distribution. The alternative is that it does not. So if we fail to reject the null, it means that we do have a good fit. If we reject the null, it means that there is not a good fit. The expected frequencies are equal, then we would, to calculate the expected frequencies, we would take the total number of trials divided by the number of categories that we have. If they are not equal, then the expected value is equal to the number of trials times p, the proportion that we would expect that outcome to occur. And that's given in the distribution. If you wanted to use StatCrunch, here are the directions for how to do that. If you have different expected outcomes or frequencies, then you need to give it a column where the expected frequencies are. If they're all the same, though, there is just an option to select that they're all the same. And these are the directions for your calculator. You do need to have your observed values in a list, so L1, and the expecteds need to be in a list as well, L2. And you'll need to tell your calculator what list you have your observed and your expected values in. So here's our first example. According to Benford's law, a variety of different data sets includes numbers with leading first digits that follow the distribution shown in the first two rows of the following table. The bottom row lists the frequencies of leading leading digits of populations of all 120 counties from New York and California combined. Test the claim that those 120 counties have populations with leading digits that follow Benford's law. So the first row in this table, these are the leading digits, 1 through 9. Second, we have our distribution. So this is the percentage that we would expect to see. So we would expect 30.1% to have a leading digit of 1, 17.6% to have a leading digit of 2, 12.5% to have a leading digit of 3, and so on down the table. The next row in the table is what we actually observed. So 33 counties in New York and California had leading digits of 1 for their population. 22 of the counties had populations with a leading digit of 2. 10 counties had leading digits of 3, and so on down the row. So here our expecteds are different, right? So 30.1%, 17.6%, and on down the row. So we need to figure out what n is. That would be the total of our observed. So that would be adding up this bottom row. So if you add up all of the numbers, 33, 22, 10, 15, 10, 9, 5, 7, and 9, you should get 120. So that's our value of n. The expected values are n times p. This row gives us p. So in order to calculate our observed, we would take 120 times these percentages as a decimal. So 0.301 would give us our first expected outcome. So that's 36.12. And you would do that for every single value there. So our observed, 33, 22, 10, 15, 10, 9, 5, 7, and 9. Then we need to calculate all of our expecteds. So I've done the first one here. You take 120 times all of the numbers in the distribution row, so all of those percentages, and that's your expected values. So I'm going to go ahead and calculate the rest and fill in the table. And why don't you pause the video here and do it yourself and see if we come up with the same numbers. So here I have all of the expecteds filled in. So you should have gotten 36.12, 21.12, 15, 11.64, 9.48, 8.04, 6.96, 6.12, and 5.52. Now fill in the rest of the row for each of these values, and it's easiest to fill in the entire row all at once. So we want to take our observed minus our expected, so 33 minus 36.12, that should give you negative 3.12, and then go ahead and square that, and you should get positive 9.7344. Now you've got this number in your calculator already, so divide it by E, our expected, which is 36.12, and that should give you 0.2695. And continue doing the same thing. I'll fill in a couple more rows and then I'll pause it and fill in the rest of the table, and then you can give it a try and see if you get the same numbers as I do. So 22 minus 21.12 should give you 0.88, and then when you square that, you should get 0.7744, and then dividing this number that's currently in your calculator by 21.12 should give you 0.0367. And we'll do one more row together. 10 minus 15 gives us negative 5. Negative 5 squared is 25. And then divide 25 by 15, our expected, and you should get 1.6667. So I'm just going to pause the video, I'll fill in the rest of the table, and then you can compare to see if we get the same values. Okay, so I have the rest of my table filled in. You might want to just pause it right here and make sure that all of our numbers match. And the last thing that we need to do once we have this rightmost column filled in is you need to add up all of the numbers in this column. So 0.2695 plus 0.0367 plus 1.6667 plus 0.9699 plus 0.0285 plus 0.1146 plus 0.5520 plus 0.1265 plus 2.1939. So when you add all of those up, you should get 5.958. And remember, the null hypothesis is always going to be that the frequency counts agree with the claimed distribution, so with Benford's law, and the alternative is that the frequency counts do not agree. With Benford's law. So again, this is the chi-squared distribution, and we could find our critical value. You would find the critical value by going to your chi-squared table. The degrees of freedom is going to be n minus, or k minus 1. So k is 9, and so we would have 8 degrees of freedom. So I'm just going to pull up our chi-squared distribution table so that we can find our critical value. We have 8 degrees of freedom, and we wanted to test this hypothesis at the 0.05 significance level. We know that because it wasn't given, and if you're not given a significance level for a test, then 0.05 is what you always want to assume. So let's look this value up. Okay, so here we have the chi-squared distribution table. And we have a 0.05 significance level. This is a right-tailed test, so this is the value, the column in the table that we want to look at is the 0.05. And we had 8 degrees of freedom. So here is the row for 8 degrees of freedom. And so our critical value is 15.507. And our test statistic is 5.958. So we can see that we are to the left of our critical value, and because it's a right-tailed test, that means that we are going to fail to reject. There is not sufficient evidence to reject the claim. That the 120 counties have populations with leading digits that follow Benford's law. So basically, because we are not rejecting the null hypothesis, they do agree with Benford's law. So that's what this means. It means that the numbers that we observed are close enough to what we expected in order for us to believe that the first digits of the populations of the 120 counties from New York and California combined really do fit the Benford's law well. So you can also, again, do this on your calculator. And if you do this on your calculator, then rounding to 3 decimal places, you will get the same test statistic. So you will get the same test statistic on your calculator, and you will also get a p-value. And the p-value that you get is 0.6519, which is much larger than 0.05, which would also tell you to fail to reject the null hypothesis. In the next example, the police departments in Madison, Connecticut released the following number of calls for the different days of the week during a recent February that had 28 days. Monday had 114, Tuesday 152, Wednesday 160, Thursday 164, Friday 179, and Saturday 196, and finally Sunday 130. We wanted to use a 0.01 significance level to test the claim that the different days of the week have the same frequency of police calls. Is there anything notable about the observed frequencies? So let's just go ahead and write these down. I kind of like to have them summarized in a list versus in the word problem, but you don't need to. You can just take it right from the word problem if you'd rather. So there were a total of 28 days. On Monday, we had 114. On Tuesday, there was 152. Wednesday, we had 160. Thursday, we had 164. Friday, we had 179. Saturday, 196. And on Sunday, we had 130. So we need to add all of these up because we need the total. And if you add them up, you should get 1,095. So one thing that we might observe just right away is that there's a slightly higher number of calls that are coming in on Saturday. So and Monday's the fewest, right? So Mondays there's only 114, and they just gradually increase up till Sunday, and then they start dropping back off. So the first thing is our expected values. So these are the same. That's what we're hypothesizing, right? That they have the same frequencies. And so that's going to be n divided by k. So n is your total. That's the 1,095. And k is the number of days that there are in the week, so 7. And you get this ongoing decimal for this number, so it's 156.429 if you only go out to 3 decimal places. But it's best not to round for this, so this is what you should enter into your calculator. You can actually enter into a list, into one of the values in the list, a calculation like this. So this is how you should just enter it, 1095 divided by 7, and hit enter in the um, list. So this is what you want to enter. You do not want to enter in this rounded number. It will throw your numbers off. So our null hypothesis is that the data fits the distribution. So that is the number of calls have the same frequency on different days of the week. And the alternative is that the data does not fit the distribution. So again, this is a chi-squared test. I wouldn't even bother using the critical value with this, since you're going to be doing it using technology anyways and you're going to get a p-value. I would just use the p-value. So in your calculator, these values will become list 1, and then you need to enter this into list 2. And you do need to have this in L2 7 times. So you need to have 7 different entries in L2. The number of values that you have in L1 and L2 have to match. If they don't, then your calculator is going to give you an error message. So again, these are what you're going to enter into L1. You're going to take 1095 divided by 7, hit enter into 7 different cells in L2. So go ahead and enter those into your calculators, pause the video right now, and then run the test and see what you end up getting. Okay, so if you entered those values into your calculator and ran the chi-squared goodness of fit test, then what you should get for your chi-squared statistic is 29.814. The p-value should be 4.021, and then at the end there would be an e negative 5. So that really is 0.0000402. So this is basically 0. So when your p-value is really low, less than alpha, and our alpha is 0.01, so as long as our p-value is smaller than that, we're going to reject the null hypothesis. So since we're rejecting the null hypothesis, what that means is that that our data does not fit into this distribution. So in our conclusion statement, so I'm going to go ahead and write that out, and then I'll start the video back up. So our conclusion is that there is sufficient evidence to reject the claim that the different days of the week have the same frequency of police calls. So the nice thing about this test is that our conclusion statement will always be one of two things. You're either going to say there is sufficient evidence to reject the claim if you're rejecting, or you're going to say there is insufficient evidence to reject the claim if you fail to reject the claim. So that's nice about this. There's only the two ways to say the conclusion statement. And we already talked a little bit about what's happening here with the number of calls. We see that the number of calls that we have on Saturday for sure is larger than any other day of the week, and that Sunday is drastically lower, and Monday is for sure smaller. And then they increase as we go through the week. So that's kind of what's going on with the number of calls that we are observing. So that is it for this video. If you have any questions about anything, please let me know, and I hope you all are having a wonderful day. Thanks.